In the previous lecture, I derived the magnetic moment and the Landé factor for an atom, and what we concluded there is that an atom has a total angular momentum J. It will then have the corresponding magnetic moment mu, which is equal to minus G mu b times J. Now, we have this collection of these atoms in a solid. So, we have a collection of these atoms in a solid. Then, if I apply a magnetic field, each atom develops a magnetic moment. And assuming that these atoms or these magnetic moments do not interact with each other. So, each atom is giving its own magnetic moment. The total magnetic moment m of the system is going to be equal to n times mu atom, where n is the number density of atoms. So, this m should be called the magnetic moment per unit volume or the magnetization. So, what I want to now calculate is how this mu atom is given as a function of temperature. Now, when this system, the magnetic moment is put in a magnetic field, let us say field B is in the z direction. So, I am going to write this as B z. I choose z direction because that is easy to calculate things with. Then the energy of each atom is going to be minus mu dot B, and this is going to be equal to plus G mu B m j times B, where m j is the z component of the angular momentum. So, I am going to have this atom which had initially a level j with j angular momentum is going to split, is going to have all these different levels. Now, you can see that if m j is positive, energy is positive. So, with m j positive, I am going to have the level go up. So, let us say this is j G mu B B. Next one is going to be j minus 1 G mu B B, and so on, and the lowest level is going to be minus j G mu B B. These are the energy levels into which this will split, and at a temperature T, the atoms are going to be distributed among these levels. However, the number of atoms in each level is going to be different. That is because the probability that energy E is occupied by an atom is going to be proportional to e raised to minus E over k Boltzmann times T. Therefore, if we put it all together, here is this atom with level given by j, and this has split into different levels. Right, let me show these levels by different colors. Each level has a different probability of occupation. So, probability of occupation of level with z component m j is going to be equal to e raised to minus g mu b mj b over kbt divided by, I have to normalize the probability, sum over mj varying from minus j to j e raised to minus g mu b mj b over kbt. And let me label this as probability that level mj is occupied. Now, the magnetic moment mu in the z direction for this level is going to be minus g mu b mj. So, if I multiply each of this magnetic moment by the corresponding probability and add it up, I am going to get the total magnetic moment. So, total magnetic moment is going to be summation of mu z for mj the times the probability that this mj level is occupied. So, let us do that. So, mu z is going to be minus g mu b mj e raised to minus g mu b mj times the applied field divided by kbt summed over mj equals minus j to j divided by summation mj equals minus j to j e raised to minus g mu b mj b over kb t. This is the net magnetic moment, and if you like, I can call this as a function of temperature and as a function of applied field B. Now, what we will find is that at low temperatures, and we are going to specify what these low temperatures are later in the next lecture when I do certain examples. Let me take this mu b times b over kbt to be much less than 1. Then I can expand this exponential term and write mu z as a function of temperature as equal to summation m, where mj varying from minus j to j minus g mu b mj times 1 minus g mu b mj b over kbt divided by summation mj equals minus j to j 1 minus g mu b mj b over kbt. Under this approximation, this is what mu z is going to be. Let me write this again on the next page. So, I have mu z as a function of temperature as equal to summation mj equals minus j to j minus g mu b mj 1 minus g mu b mj b over kbt divided by summation mj equals minus j to j 1 minus g mu b mj b over kbt. Let us look at the first term in the numerator. Summation mj equals minus j to j is equal to 0, because there are equal number of negative and positive terms, and therefore, I can write mu z t equals summation mj equals minus j to j g square mu b square b over kbt times mj square divided by the second term in the denominator will be 0 and I get 2j plus 1. Now, I use the series sum formula for summation mj square j equals 1 to j is going to be equal to j plus 1 times 2j plus 1 divided by 6, and I will substitute that in the expression above. Now, this will go in here multiplied by 2 because I have mj going from minus j to minus 1 and mj going from 1 to j, and 0 anyway does not contribute. So, I get mu zt as equal to g square mu b square over kbt times b times 2 times j plus 1 2j plus 1 divided by 6 times 2j plus 1, and I cancel this term, and this 2 goes with 6 and gives me 3, and therefore, I end up getting mu z t as equal to g square mu b square j plus 1 divided by 3 kbt times b. And if I compare this with the expression for susceptibility, mu is equal to chi magnetic times b divided by mu 0, I get chi m equals n mu 0 g square mu b square j plus 1 divided by 3 kbt, where n is the number of atoms per unit volume or per mole, depending on how you want to write, what you want to calculate chi m for, and this equals C by T, where C is a constant. So, what I have found through this calculation is that when I put this collection of atoms in a solid and the atomic magnetic moments are not interacting with each other, I get the magnetic moment m per unit volume, which is also known as the magnetization, as equal to some function c divided by t. It is inversely proportional to t. This is known as Curies law. What does that law say? It says that paramagnetic susceptibility is proportional to 1 over t. It goes as some constant divided by t. As temperature goes up, the paramagnetic susceptibility goes down because the levels start filling roughly equally at very high temperature. So, this is the introduction to paramagnetic systems. Where what we have done is we have taken an atom, seen how the levels are split under Russell-Saunders or Ellis coupling when a field is applied, and then populated them according to the Boltzmann's law, and using that we found the paramagnetic susceptibility. So, to conclude this lecture, what we have found is that atom with angular momentum, and when I say angular momentum, I mean the total angular momentum. So, let me specify total angular momentum J has magnetic moment mu equals minus G mu B J, and when I apply magnetic field, these levels due to different z component of J split and populate differently, and that leads to a paramagnetic susceptibility chi m equals some C over T, which is known as Curies law. How these J's and L and S are calculated will be the subject of next lecture.